Hello everyone, my name is Said and today I want to present our work entitled Astra-sim enabling software hardware co-design exploration for distributed deep learning training platforms, and it's a result of collaboration between our lab, Synergy Lab at Georgia Tech, and Facebook and Intel. To begin with, I want to define the training and what distributed training is. So, training a neural network involves using a training data set to update the model weights to create a good mapping of inputs and output domains. Um, and In recent years, training time has been constantly increasing, mainly due to three main reasons. One is that DNA networks are becoming bigger, um, such as BERT or GNMT, the recent um, DNNs that um, their size is increasing. And also the other reason is training samples are becoming larger, such as DLRM, and also the Moore's law is that, meaning that we cannot further improve the performance of a single core. And the solution for them is to use distributed training to overcome the long latency of retraining workloads, the recent training workloads of big DNN models. And there are some certain challenges with distributed training. One is, and one of the main challenges is the communication, because it's inevitable in any distributed training algorithm. And the communication pattern also depends on high level characteristics of the training loop. Um, for example, whether we use synchronous or asynchronous training, or what type of parallelism approach we use, data parallel, model parallel, or mixture of these two called hybrid parallel. And the question is that the problem? The short answer is that it depends, and it depends whether we can hide the hide the communication behind compute or not. So here is some background work about the terms we mentioned earlier. So here it shows the difference between synchronous and asynchronous training. In asynchronous training, each node, irrespective of the other nodes, generate the weight gradients. It updates the weight and quickly starts the next training iteration. However, in synchronous training, each node waits for the other nodes to finish their weight gradient computations. They then exchange the weight gradients and then update the weights and then start their next training iteration. This means that they work on the same version of the weights in any training iteration. And in this paper, we focus on synchronous training because it's been observed that it has better convergence rate. And here it shows the data parallel training parallelization strategy, where the nodes, each node is assigned a portion of the input training data, and they all have all of the weights of the DNN model, and then during the forward pass they work on their corresponding input gradients. They produce the output activation, and no communication is needed. However, in backpropagation, for each layer, each node, once it computes the weight gradients, it needs to exchange these weight gradients with the other nodes to globally reduce these weight gradients, and then they update their weights according to these globally reduced weight gradients. And this means that we need communication for um, weight gradients. And here it shows the model parallel training parallelization strategy where the model is split across different compute nodes, and all of the nodes work on have the um, and work on the same input samples. And here, even during the forward pass, we need to exchange the output activations because since each node has a partial weights, it can only generate a partial output activations, and because it needs the whole input output activations for the next for processing the next layer, these output activations need to be communicated, and hence we have a blocking communication in forward pass. And in the backpropagation, we need to also again exchange the input gradients, because again each node only can generate partial input gradients, and it needs the whole input gradients to be able to go to the previous layer in backpropagation. Again, we have blocking communication. We can then, using model parallel or data parallel, create a mixture of these two. For example, we can create super nodes where between these super nodes we can have a data parallel training strategy, while between the nodes within a super node we have model parallel, and we can have various flavors of these, and all of them are categorized as hybrid parallel. And as you can see, there could be different parallelization strategy, and all of them have different communication patterns, but it turns out that all of these communications in the low level can be handled using a set of primitive collective communication patterns. And the most common collective communication pattern in training workloads is reduce, where at the beginning, at the beginning each node starts with a partial result, and at the end of the reduce, all of the nodes have globally reduced data, and each node has a copy of the globally reduced data. And sometimes in some training workloads we also observe the all-to-all collective pattern, where each node starts with the data, where each portion of data belongs to a specific destination, and it needs to send each portion of that to its specific and its corresponding destination. And depending on the training workload, there could be one or a mixture of these collective communication patterns needed for handling that training workload. And again, we can have some research questions here. What determines the runtime for a collective, and what is the compute communication ratio during distributed training? To answer this, we need to take into account that there could be many different ways to implement these collective communications, and these collective communications, usually the optimal way of doing that is also network topology dependent as well. Here I included a ring-based or reduce collective communication pattern, where all of these nodes are connected through a network, a network of ring. And here in this case, in this specific way of doing all reduce, that is called ring based, the data can be divided into 4 messages, and in the first phase of this all reduce algorithm, each node just sends one message to its neighbor, and then it does and once it receives a message from another neighbor, it does a local reduction with its own local data, and then forwards that data. So this process continues until this phase, that at this step each node has a portion of globally reduced data. We call this phase after this phase we call it data is reduced scatter, and now each data broadcasts its portion that is globally reduced, and we call this phase all gather. And after this step, all of the nodes have um, a version of data that is globally reduced, and this phase is called all gather. So in general, um, we can think of all reduce as a reduce scatter followed by all gather. And then we can create more sophisticated topologies, and hence we can have multi-phase collective communication algorithms as well. For example, here in the left we have 3D torus topology where we have three dimensions, and in each dimension we can run those primitive collective communications. And in the right we have all-to-all based topology, and for example you can think of the way that all reduces can be handled in all-to-all topology. Um, um, we can divide this all reduce into three phases. The first phase is doing reduce scatter within a package, then do all reduce across switch, and then do all gather within a package again. And this, the similar steps can be done in Torus 3D, where all reduce is divided into four phases. The first phase reduces gathered within a package, then all reduce across rows, all reduce across columns, and then again all gather within a package. So we can create multi-phase collective communication algorithms. So the main challenge is that how we can model and evaluate the communication effect. As we saw earlier, there are many parameters playing role here, and it's a complex problem, and we can think of it as three different layers that affect the communication performance. The first layer is workload layer, where it defines the training loop and the orders and dependency between communication and computation tasks. And the middle layer is called system layer, where it handles the collective communications and execute the collective communication algorithms once the workload layer issues communication. And then at the bottom layer we have the network layer, where it handles the actual data movement between these different compute nodes. What we realized was that the first two layers, there are not too many tools proposed to cover these aspects in the simulation domain. However, there are many network simulators already available for network simulation. So that was our motivation to develop the Astra-sim, where it implements the first two layers, workload layer and system layer. It also has a network API, where is the point of interaction between Astra-sim and any network simulator, and any network simulator that implements this network API is able to communicate to work with Astra-sim. And currently our workload Astra-sim workload layer supports different parallelization strategies, and one can easily add new arbitrary training loops to it. Our system layer also supports different collective communication algorithms, and it is also possible to add new collective communication algorithms to it as well. Then there are at this version there are two network simulators that supports this network API interface of Astra-sim, NS3 and Garnet. We modified them to implement these API, and the details of these network simulators are available in our GitHub web page. And then The next question is why even we need simulation. There are two main reasons for that. First is that in the design space exploration, many parameters, especially the hardware parameters, may not be changed because their hardwares do not exist. And the second reason is that the analytical model might be insufficient because the network can be congested, and the analytical model is not able to capture these effects. And we did a very simple case study where we just simulated a simple reduce on our simulator and compared the results with on a simple analytical model, and we found out that in the cases where networks become congested, their difference might be orders of magnitude. That's why we need simulation methodology, because it enables us to have a flexible tool to do design space exploration, and also it is more accurate compared to the analytical model. Then here it is, the simulation methodology is presented. We used scale sim simulation for obtaining the compute times. We used Garnet backend, and our DNN models were transformer, ResNet, and also some micro benchmark for single collective. And our target systems were Altwall and 3D Torus. And here the 3D Torus and Altwall topologies are presented. The details of the namings for these topologies are included in the paper. And this is the first result, the micro benchmark, Torus versus Altwall, and for single collective. And it shows that the Altwall topology in general works better for all-to-all collectives. However, for R-reduce in our target systems, the R-reduce works better for Torus topologies. Then here we have the effect of 1D, 2D, 3D Torus topology for 64 nodes, and it basically shows how communication might be affected as we connect these 64 nodes with 1D Torus, that is a ring, to 2D or 3D Torus. And this result is for a single R-reduce, and more details on that can be found in the paper. Here we have this impact of asymmetric hierarchical topology. It means and it shows how communication might be reduced if within a package we have higher bandwidth. And also it shows what happens if we modify the algorithm based on this asymmetric bandwidth, and we can further reduce the communication time. Then here we have the raw communication delay for layer-wise raw communication delay for each transformer workload. And as you can see here, we used a hybrid parallel approach, and because of this certain synchronizations we need for this hybrid parallelization workload, parallel workload, we see that these latencies are very homogeneous across different stacks of transformer layer. And here we have data parallel layer-wise raw communication delay for ResNet, and you can see that the raw communication delay is dependent on both queuing delay for the communication, and also the layer and the communication size for each layer as well. Here we have end-to-end latencies, which means the exposed communication latency. Exposed communication is the amount of communication where the algorithm is forced to wait because it needs that communication to be finished, and we couldn't hide that communication. And it also shows the total computation for that layer. And here we observe that only the first layer, the communication corresponds to the first layer, is exposed. Again, more details on that can be found in the paper. Then another set of stats that Astra-sim provides is a very detailed set of stats about each phase of the collective algorithm for each layer, um, such as queuing delay and the delays spent in the network. And all of these delays, again, the details on that is again presented in the paper. Then here we show some ratio of total exposed communication to total exposed computation to total computation for different network sizes. We can see that as we increase the number of nodes, the ratio of exposed communication latency increases for 2 cross 2 cross 2, which is 8 nodes. We see that less than a 10% is communication, while in 128 nodes, more than 20% is exposed communication. Here it also shows what happens, for example, if the compute efficiency per core increases, and you can see for 4x in compared to the baseline, if the compute efficiency increases by 4x, then we can see that the exposed communication also doubles. And using Astra-sim, one can find out what happens as these hardware parameters or even software parameters changes. And here it shows the next version of Astra-sim that we are working on, and we are planning to add the memory API and compute API to it as well, so that we can increase the accuracy of simulations and also capture the congestions happening in the accelerator memory because of the computation and communication tasks. And more reports on that can be found, and the updates on that can be found in the GitHub page. In the summary of to sum up this presentation, we showed that the design space exploration for best hardware software platform for training workloads is quite large, and our simulation methodology provides a convenient way and also accurate way of exploring this space. And we studied the performance of collectives and real workloads across different topologies and hardware software parameters, and we showed that how communication increases as the size of the network increases or compute accelerator efficiency increases. Thank you for attending this talk.